Right, good morning, everyone. We'll just give it a few seconds here until all the people that registered are getting into the webinar. Then we'll start the show. Okay, seems we have a good amount of people joined in. Good morning, everyone. My name is Amin Menena. I'm the Technical Services Coordinator with the Municipal Engineers Association, and I'll be your moderator for today's webinar. This webinar is in collaboration with the Ductile Iron Pipe Research Association, and our presenter today is Sam Gosson. Sam serves as the Regional Director of Canada for the Ductile Iron Pipe Research Association. Sam helps utility managers, engineers, operators with system planning and design, installation and asset management questions related to iron pipe. Sam received his Master's of Science from Memorial University of Newfoundland in 2016. He is a licensed professional engineer in Ontario. Prior to DIPRA, Sam has served in various roles in infrastructure industry as a field engineer, production engineer, and a project manager. His experience in trenchless technology include pipe condition assessment, pipe rehabilitation, slip lining, tunneling, and horizontal directional drilling. Sam will talk to us today about the asset management strategies for ductile iron pipes. Sam, the floor is yours.
Oh, thank you, Amin, for this kind introduction. Good morning, everyone. I assume everyone is in Ontario, but if you're not, good afternoon. But I assume all of us are in Ontario. So thanks, Amin, for the introduction. Today we'll be discussing asset management strategies for ductile iron pipe. It is a very interesting topic that we talk a lot about in Ontario and across North America in general. A little bit about myself. I'm Sam Gosson. I'm the Regional Director for Canada for DIPRA. I'm based out of Ottawa, but cover the entire country. So I'm a flight away from every municipality and engineering office. DIPRA is a non-for-profit organization. We were founded in 1915 as CIPRA, and then we became DIPRA as we transitioned from cast iron to ductile iron pipe in the 60s. We work closely with our members. In Canada, we have Canada Pipe and McQueen Canada, McQueen Canada also owns Canada Pipe, BB Synchro, and Cloud Valves. So they manufacture everything from iron pipes, valves, and fittings. In the States, we work closely with McQueen Ductile, American, and US Pipe, who also make ductile iron pipes, valves, and fittings, and we take care of the research for them. It's a huge industry. We make millions of feet of ductile iron pipe every year, from 3-inch all the way to 64-inch in diameter. DIPRA has 5 regional engineers, 4 cover the United States. We're adding 2 this year, so we'll have 6 in the United States. And then myself in Canada, obviously the smallest territory on that map. So in this presentation, we'll be discussing some history on iron pipes, and most of you may hear about cast iron and ductile iron pipe, but may not know the difference between both material. It is one of the most historical products that are still existing and being sold in the market, although a lot of products that started in 1800s and 1700s are no longer used. We will deal with the facts that nothing destroys iron but its own corrosion. So we'll discuss corrosion, how it happens, and how we can control it and prevent it in many cases. Asset management strategies, how we could stand the test of time by designing, installing, manufacturing, installing, and maintaining a water system for 100 years of service. Asset management, how do we define asset management for metallic pipes, especially cast and ductile iron pipe, and what kind of data we look for. As a pipe professional, been in the industry for close to 10 years now, what do I look for when I look at a pipe? And especially when it comes to cast and ductile iron pipe, there's a huge spectrum of data that we need to consider when analyzing and assessing the condition of that main. And that would drive a decision of either repairing, rehabbing, replacing, or renewing that main. Evaluating for new construction, what kind of risk-based approach do we take these days as iron pipe professionals and even municipal engineers across North America in handling the risks of corrosion, and how we could monitor those risks and actually weigh the risks, the consequence of a failure in regards to the likelihood of corrosion. So we'll discuss those in the last part of this presentation, and this is really related to new construction more than existing infrastructure. And the last part is 2 examples from an AWA study and an interesting graph from the ISO standard for asset management of water systems. With that, let's get started. So some of you may have heard of this pipeline. This is one of the oldest cast iron pipe in service in the world. It was built by King Louis XIV of France, and those pipelines were built to service the Palace of Versailles. So King Louis XIV of France had to carry water from Marly Ancien all the way to Versailles. So they built those twin pipelines that you see on the right side of this slide. These 2 pipelines, folks, serviced for 330 years. And they were decommissioned in 1990. So how come these pipelines serviced for so long and the return on investment is astronomical in this case, where some of the iron pipes installed, a lot of it in Ontario in the 50s, 60s, 40s, even in the 80s, without corrosion control, suffered from corrosion and had so many issues, and they were ultimately replaced by cheaper, weaker pipe materials that we deal with today, where other municipalities across North America are still relying on ductile iron pipe. So there's a lot of variation of iron pipes, where they were installed, how they were installed, and their condition today. Is it the case of King Louis XIV of France only? No. Today, we have utilities across North America still benefiting from the investment they made 100 or 150 years ago. And those are members of the Century Club and the Sesquicentennial Club. So some utilities, folks, over 600 cities across North America still have iron pipes in service for over 100 years. And more than 30 utilities have iron pipes in service for 150 years. The latest addition to our Sesquicentennial Club in Canada was the City of St. John in 2022. The City of St. John joined the Sesquicentennial Club with iron pipes in service today for 165 years, still pushing water in downtown St. John and providing that amazing return on investment. And if you work for a utility and still have iron pipes for more than 100 or 150 years, please reach out to me and I'll be happy to provide you with a form that you could fill and you could join that club. It just shows that the investment you have made a long time ago that's still benefiting your taxpayers today. It is something that we feel proud of, and we want to continue to do so with many utilities across North America. So this is all good news. Why? Because it's not only 650 cities that are relying on ductile iron pipe and cast iron pipes longevity. There are many cities across North America still reliant on ductile iron pipe today. And I could name a few, some of the most expensive real estate in North America, New York City, Vancouver, Boston, Philadelphia, all the way to the East Coast of Canada and Halifax. Those cities still relying on ductile iron pipe as a material of choice today. They transitioned from cast iron to ductile iron pipe, and they have millions of feet of ductile iron and cast iron pipe delivering water in their cities today. So there's a big reason and good reason why the cities rely and invest on in ductile today and in the future. So this will continue, hopefully. However, we had some issues with cast iron pipe, and especially if you're in Ontario, there are many issues in Ontario where a lot of cities suffered from breaks, a lot of breaks with ductile iron and cast iron pipe, mostly on the cast iron side. And we could actually differentiate between two categories here. The cast iron mains installed from the 1820s all the way to 1960s, mostly I would say 1850s or 1860s in Canada up to 1960s, so about 100 years. Those iron pipes, cast iron pipes, had a variety of joints. Obviously, they have no corrosion control on them, and they were made differently too, because the manufacturing of those pipes evolved over the years. So some of the issues we encounter with older iron pipes with, and when I say older, installed in 1800s and 1900s, that are early 1900s, that were not protected, obviously, from the inside or the outside, suffered from internal corrosion, and that's tuberculation. I'll talk about that in the next slide. That was fixed with ductile iron pipe by providing a lining on the inside. External corrosion, obviously, Uncle John, when he installed pipes in 1800, did not worry a lot about corrosion. Today, we want to make sure the investment we put on a pipeline today will bring us a return for 100 years of service. So that's why in the 1960s, 70s, all the way to the 80s, corrosion studies were evolving, and there was a lot of research happening in the corrosion space. Today, we know how to protect iron mains. We know how to provide 100 years of service for utilities and pipeline owners. Mechanical failures, these were common also with cast iron pipe, and I'll show you in the next few slides what's the difference between gray iron and ductile iron, because they are different materials in terms of mechanical properties. Although they may look the same, they may behave the same in many ways, and they may have the same OD and ID in many cases. However, they are different materials, and that change in microstructure between ductile and cast brings a lot of differences to the performance characteristics of that pipe. So you may have some brittle failure modes with cast iron pipe, and I mean by that joint separation, circumferential breaks, mostly barrel bending failures, because the pipe was brittle. It will break under a bending moment, where ductile iron pipe is very flexible and is ductile, so basically has high ultimate strengths, yield strengths, and modulus of elasticity. Different materials, I'll show you that in the next slide. So what's the difference between ductile and cast? And that's a question I always get. People think, a lot of engineers still think that the material is the same. We just changed the logo on the pipe. That's not true. Ductile iron is an evolution of gray iron pipe. And what we did was very simple, but it made a huge difference. We added magnesium and silica to the melted iron. So when we melt gray iron pipe, you add magnesium and silica, you get that fireworks that you see on that left side of the slide. And by changing that microstructure, you see how the microstructure, the graphite shape is different from a flake shape into a nodular shape. And that change in microstructure between gray and ductile iron changes the mechanical properties and create a ductility and high ultimate and yield strengths as well, compared to a brittle material with gray iron. Keep in mind that modern ductile iron pipe is a sustainable product. We don't go mine for iron ore to create ductile iron pipe. We actually buy recycled cars and steel and scrap metal, melt it and recycle it. On an average, we have over 1 million car that is recycled in one of our member companies' facilities, where in North America, over 12 million cars are recycled every year. And then we use that scrap metal to create brand new ductile iron pipe. So once the melted iron is poured into this casting trough, we cast the ductile iron pipe with 18 or 20-foot sections, depending on the manufacturer, and then the final product will look obviously like this. I don't recommend that you treat pipeline like this, folks, like you see in this photograph, but this shows you the strengths and ductility of ductile iron pipe. You can't do that with cast iron, and obviously you can't do that with other pipe materials like plastic, for example. You could see from this graph the difference in mechanical properties. Ductile iron and grade B steel are very similar in regards to mechanical properties, high yield strengths, ultimate strengths, great modulus of elasticity, and a 10% elongation, where a gray iron pipe was brittle, did not have elongation. And obviously, if we compare all three to plastic pipes, radically different properties for PVC and HDPE, with much lower yield strengths and ultimate strengths. There is a room for every product in the market and an application for every product, but you need to understand the difference. They are not apple to oranges, and they are not, sorry, apple to apple. They are apple to oranges comparisons. So when it comes to corrosion, folks, we always think about what is corrosion? And it is actually the cancer of metals on the ground. And when I say cancer, it happens over 30, 40, 50 years, and you may not know about it until it's too late. So today we do preventive maintenance and we do preventive measures. We eat well, we have a healthy lifestyle, and we prevent cancer. And then we do the same thing with pipe these days. We treat corrosion from day one by doing proper corrosion control measures, following a design decision model that I will discuss in the last few slides of this presentation. However, we still have to deal with existing infrastructure that was built in the 1800s and 1900s without corrosion control, and we have to either make a decision on replacing it, rehabbing it, or keeping it until it fails. So when it comes to corrosion, basically, we need to understand the corrosion is the reaction of a metal with its environment, as simple as that. So if the environment is corrosive, the pipe will actually react with that environment and will fail over time. However, if the environment is not corrosive, you could install any metal, including ductile iron pipe, in those kind of soils, and they will be there forever without even corrosion control. So we need to understand the environment before we judge whether the pipe will be there for 100 years or not. And that's what we did over 70 years of research with DIPRA and a lot of utilities across North America. I told you about internal corrosion. That was an issue with unlined cast iron pipe. Again, back in the days, we did not have linings on the inside of the pipe. So that if the water was hard, and what I mean by that, you have acidic water or alkali water, depending on the pH, you may have an interaction between the water and the iron pipe on the inside, which caused that tubercle on the inside of the pipe. Tuberculation is the reaction of that water with the iron, and that forms over time. Obviously, it will reduce the flow of the pipe and water quality. How did we solve that over the years? We added cement mortar lining. So every stick of pipe today that leaves the foundry in all our foundries across North America will have cement mortar lining. Cement mortar lining will act as a barrier between the water and the pipe, and will cut off any corrosion that may occur between or contact between the pipe and the water. Okay, so this is a lining, it's a barrier that we added, and obviously everything that we add on ductile iron pipe is NSF 61 approved from the inside and outside, so the pipe is fully safe to be in contact with water. It has to meet AWAC 104 standard, so unless you otherwise specify in your project for certain applications, every pipe that leaves the foundry will have cement mortar lining on it. We have tested the longevity of cement mortar lining over 46 flow tests across the United States, and we came up with that chart that you see here with all the Hazen-Williams coefficients, and that's why the recommendation for C140 for new ductile iron pipe is very consistent because we have tested it over the years. And so if we're designing a new water main with ductile iron pipe, we use an Hazen-Williams coefficient of 140 for the hydraulic analysis. You will do the same for a steel pipe with cement mortar lining on the inside. You would do the same for a concrete pressure pipe as well. So all the cementitious pipes, including ductile iron, will have C140. However, when I told you corrosion will happen on metallic pipes, it's not going to happen only on ductile and cast. Any metallic pipe that you see on the ground, including steel pipe, concrete pressure pipe, and quite frankly, every component of a plastic pipe system. So let's say you're using PVC in your system or HDPE, but you're still connecting to ductile iron valves, ductile iron fittings, T's, Y's, elbows, and ductile iron hydrants and their barrels. So iron is everywhere underground. Even the fasteners that we put on plastic pipes are made out of metals most of the time. So the fasteners should be protected as well, and they are susceptible to corrosion if soils are corrosive and you didn't treat corrosion very well. So you need to make sure that it's not only the pipe that's taking care of corrosion, it's all the components on the ground. So that's why we have a lot of research on corrosion control, not only on the pipe, but the entire system of ductile iron pipes over the years. This is one of the earliest installation of ductile iron pipes in the 60s. You could see, look at this photo, folks, and you could see how beautiful the pipe is looking after 60 years. You can still see the hand markings on that pipe. And so how come this pipe lasted for so long and it's still in service? Still looks brand new, no corrosion control on it, and very good soils. And what I mean by that, look at the resistivity, 3,000 to 7,000 ohm centimeter, which means very low conductivity of current in that kind of soil. Okay, low conductivity, it means high resistivity, means low corrosion current, and that means the electrolyte is not as aggressive for ductile iron in those areas. You bury that metal in that kind of soil, it will be there for centuries, no question. Okay, however, we have other cases where we see that a lot of it, and that's a blowout hole in a corrosive environment. What we define those environments as: low resistivity soils, high anaerobic bacteria, dissimilar metals. You may have a swamps with fluctuating water table, salt water, stray current from external sources. Those are very rare, but they happen too. When a current jumps on ductile iron pipe from an existing natural gas line and leaves ductile iron pipe on another end, it will take metal with it. So we need to understand what caused that corrosion. And if we see corrosion in those areas and you're replacing that main, you want to make sure that you do proper due diligence for a pipe replacement project. And not only for the pipe, like I said, for the components in the area. Okay, because you already have an indication as an asset manager that corrosion is a hazard in those neighborhoods, cities, or even regions. Okay, so understanding pipe corrosion control is a very unique topic, and I'm not gonna get into it because we don't have 2 hours today. And I'll be happy to chat about it individually if you have any questions later on. But to simply understand corrosion, you need to understand that you need 4 elements: an anode, a cathode, a return current path, and electrolyte. If one of these elements do not exist, corrosion simply will not occur. Okay, the electrolyte is the most important factor in this equation because that's the soil. That's what we cannot control. It is existing, and we're bringing the anode and the cathode. Those are different parts on the pipe, and the return current path is on the pipe itself because it's a metal. You're putting that anode, cathode, and return current path in the electrolyte, and that's the soil. So we need to control that electrolyte around the pipe, and by doing so, either we put polyethylene casement on the pipe, or we could put sacrificial anodes or zinc coating or cathodic protection. There are many ways to do that, but the entire goal is to control the electrolyte, and you control that corrosion cell around the pipe. If the electrolyte is not corrosive, simply you're burying ductile iron pipe in sandy soils or on rocks and boulders, this electrolyte has a very high resistivity and it's not conducting current anyways. So the pipe does not require any corrosion control. So not every soil is corrosive. How do we know if soils are corrosive? We know that by testing soil samples, folks. Very important. Like I said, Uncle John in 18 and 1900s did not do that. This started in the 50s and 60s, and today we do due diligence on every water main that we install these days. So what kind of parameters you need to test in the soil sample? You need to measure resistivity, most important thing, how conductive that soil is for current, pH, redox, sulfide, and moisture. Historically, we used to use this 10-point system, which you could still use as an indication on whether this soil is corrosive or not. We measure total point for that soil, and if your points are above 10, this soil is deemed as corrosive to iron. You have to protect this main, and if the points were less than 10, we do not have to protect that main. Today, we have the design decision model that is an evolution based on this 10-point system, and I will discuss that in the last part of this presentation. How did we learn about corrosion at DIPRA and our member companies? Through our test sites. We have test sites across the United States, and we have one in Canada as well, where we buried iron pipes in different environments, and we tested them over the years. Some of the most aggressive environments, Atlantic City and Everglades, swamps, water table, very low resistivity, and anaerobic bacteria. Perfect environment for corrosion, folks. You bury an iron pipe in that environment, it will be gone in 15 years. You bury an iron pipe in Wisconsin where resistivity is 6,000 ohm centimeter, it will be there for 3 centuries, 300 years without corrosion control. So every environment is different, and if you have a failed pipe in your system, doesn't mean your neighbor in another city will have a failure as well, okay? So pipes age differently, and age is not an indication on condition of pipe. And that's the purpose of that webinar, actually. So when you look at resistivity, you look at and you notice a difference in resistivity between those soils, and that's why we chose this environment to test iron pipes for 60 years, because every environment will be different for iron pipe. So Everglades is one of the most aggressive environment. We call it nasty soil in other language, but some soils are amazing when you have 6,000 ohm centimeter compared to 150 ohm centimeter resistivity in the Everglades. Those soils are very common. We see a lot of those in Canada, but in the prairies, for example, you're closer to, and in some parts of Ontario, you have aggressive soils, also called hot soils, which could be close to a 500 to 800 ohm centimeter. Okay, this is a uniquely severe environment at 150 ohm centimeter, where you bury any metal on that ground will be gone in a few decades. So since 1952, we started research on corrosion control, and we learned a lot about polyethylene encasement. Why? Because polyethylene encasement is the most economic and effective means of protecting iron pipes. Basically, what we're doing, we're putting a bag on the pipe and controlling the electrolyte. So the electrolyte around the pipe is a homogeneous electrolyte, same in nature, where you don't have anodic and cathodic areas around the pipe. So you create that atmosphere or environment around the pipe that is actually consistent and will control corrosion for many years. Because corrosion will always happen. It is a reaction with of a metal with its environment. But corrosion rate is what matters, folks. A corrosion rate of 0.001 mils per year may lead you to a 400-year service, right? A 0.2 mil per year may lead you to, or 2 mils per year may lead you to a 20 years of service. So we need to understand the difference, the type of soil, and what we're dealing with exactly. So we learned a lot about polyethylene encasement. We examined over 1,600 specimens across the United States, so we understand the longevity and efficiency of those corrosion control systems. Why do we like it as an industry? Because it is inexpensive and is an unbonded coating on the pipe, so it does not create corrosion cells on the pipe. Corrosion will be distributed it yields to soil stresses, and it is a passive protection system. I don't have to maintain it every 20 or 30 years, like sacrificial anodes, for example, that I have to come back and maintain and replace. And it does not deteriorate underground. And I'll show you an example of a dig up where we dug up a 60-year-old polyethylene cased pipe in Lafourche Parish, Louisiana, last year. So it took about 20 years for polyethylene casement to start to be standardized from the day we started research to 1972. So if your pipelines were installed before 1970s, even in the 1970s, there is a great chance these pipelines were not protected at all, okay? They were buried as is. We call them bare pipe, which means those pipes did not have corrosion control on them. Some municipalities put anodes on them back in the days, or came back and put anodes on those pipes when realized, oh, we need to take care of corrosion. But it took about 20 or 30 years for many utilities to understand corrosion control. And that's why if you're dealing with problematic iron pipes, you're probably dealing with those pipes that were installed between the 1960s to 1980s kind of time. Today, it is a different ballgame that we play. So that's why it is standardized. I invite you to go through this standard and read it, folks. AWA C105 standard. It's not only about polyethylene encasement, but will teach you a lot about corrosion control and corrosion evaluation of iron pipes and soil types as well. So if you have a chance on a Friday afternoon, please go through it. And if you have any questions, you feel free to reach out to me and I'll be happy to answer them. Like I said, we don't protect ductile iron pipe only. All your metals on the ground, most of them are actually made out of iron. Your valves, your hydrants, your apprentices, and I call this the ugly Christmas gift wrap. Okay, why? Because you have to wrap that fitting. It's not going to look pretty, but it actually what you're doing, you're creating that wrap around the pipe. You're creating a homogeneous electrolyte around that pipe, and you're protecting it. It's just creating a dielectric barrier between the soil and the pipe. There are other options for fittings, valves, and hydrants out there. They tend to be more expensive, but if you're worried about whether you should protect or not, simply put polyethylene encasement on it if you're considering not to wrap it at all. Okay, but if you have already a program of installing anodes or mastic tape on those petroleum tapes on those fittings, valves, and hydrants, then you're free to do so. What matters to me is you protect it no matter what. So over the years, in 2013, we came up with a new polyethylene encasement bag, and that was called VBio Enhanced Polyethylene Encasement. Basically, the bag, it has similar properties to standard polyethylene encasement. It has to meet AWA C105 standard. However, this bag will have two layers that are co-extruded with the bag, and those layers are an antimicrobial and a corrosion inhibitor. So they help control the environment, the electrolyte between anything that gets under the wrap from water that we expect to get on the wrap. It's not watertight, it's not airtight. However, we don't want to exchange that water in and out. So we want to make sure that the electrolyte goes passive after a while, once we consume the oxygen and through surface oxidation on the pipe, actually. So some of you may have heard of zinc coating. It is not a new technology. However, it's getting more and more popular in the States and in Western Canada. Zinc coating is basically an anode that we install on the pipe from the foundry, in the foundry, sorry. So during the manufacturing process, we melt two zinc wires at 787 Fahrenheit, 99% pure zinc, and then we use compressed air to blow the zinc on the preheated pipe at 175 degrees Fahrenheit. So this zinc will adhere on the surface of the pipe and will create an anode on the pipe with a 200 gram per meter square density. So this zinc actually acts as an anode on the pipe. It is a sacrificial metal that will tend to protect itself to protect the iron. So it sacrifices itself to protect the iron. So how does it work? Basically, like I said, it's an anode that you put on a pipe. And the question would always come, can I use it with polyethylene encasement or without it? You should use it with polyethylene encasement, because that's how you extend the life of an anode. If they protect that anode basically on the pipe, and you protect the pipe, you're extending the life of that anode. So in areas where this soil is extremely corrosive to iron, it's a high risk environment where the main is very critical. There are many variables that we could think of where we could consider zinc coating with VBio. We're studying it right now in our test sites, so we're close to a 10-year research with zinc coating, but the results are phenomenal so far. We like it. It is a belt and suspender situation where you put zinc and VBio, but it is an ultimate solution to installing anodes on every stick of pipe, or putting cathodic protection on those mains. So let's talk a little bit about asset management, and that's really the goal here. All what I told you so far is an introduction on what we should do with asset management of water mains. As you probably know, most of you might be asset managers. What we care about with metallic pipes, we need to direct, control, and optimize those infrastructure assets, and we want to make sure that we include the cost of performance of those assets through their design life. Okay, and what are the two main goals as water professionals? We want to provide safe drinking water to utilities and our taxpayers, our residents, and we need to make sure we provide readily available water for firefighting purposes. So your water main should not be only reliable, but should be resilient and sustainable at the same time. So when you need it, when a fire occurs and you need that water main, it is there available for you. Okay, so keep those two purposes in mind, because as water professionals, that's our main target and purpose and mission in our industry. So when it comes to life cycle costs, you're thinking about planning only and designing and constructing that main, but you also need to think about operating, maintaining that main, rehabilitating that main down the line, and possibly disposing it. Okay, so keep those all elements in your design and evaluation of pipe materials, because pipe materials are different, they fail differently. Metallic pipes fail from corrosion if you don't treat corrosion from day one, and plastic pipes, for example, they would fail from stress, which is much harder to control down the line. So keep things in mind. Every material has its role in the market, and every material has its purpose. So we want to make sure that we address corrosion from day one, so we ensure the longevity of 100 to 200 years of service. But when it comes to existing pipelines, folks, you need to think a lot about performance data. I'm not going to get into the strategies of how you manage and assess that data, because every utility may have a different process or system in place. But what I care about really is what pipe data am I looking at as a pipe professional and a pipe engineer. I'm looking at performance data of that water main, for example, the failure rates, the break rates, the age. Although age is not a factor, it is an indicator of possible conditions. We don't need to confuse between age and condition. An old main does not mean a bad main. An old main could be an excellent water main that you could rehab and maintain for another 100 years. Okay, so do not confuse between age and condition. So why do we need performance data? Because it will give us a lot of information on financial decisions down the line, either preventive maintenance, rehabilitation, or replacement. So what kind of data we like to look at as pipe professionals, and especially myself as an iron pipe expert? I like to look at criticality of that water main. Is it low, medium, and high priority? Is it a 3-inch water main or a 64-inch transmission main ductile iron pipe? Two different materials. Same material, two different pipelines in terms of priority. Failure rate, number and frequency of breaks in that area. Do I have a trend of failure rates in that region? So I have to focus on that area more than another neighborhood. Installation date, like I said, an indicator of possible age and possible corrosion. Now, if I measure and I do condition assessment on that main, and I know that corrosion rate is extremely low, and it's already been in service for 100 years, there is a 99% chance that this main will be there in service for another 100 years, because you know the corrosion rate, you know how long it's been in the ground, and the soil did not change because you did not remove that pipe out of service. So pipe material, understand the difference. Gray iron pipe may have circumferential break, mechanical failures. Ductile iron pipe, most likely not. It will not fail from mechanical failures. It will fail mostly from corrosion if it was not protected from day one. Like I said, 60s, 70s kind of age, where those mains were installed without proper corrosion control in many areas across Ontario. Corrosion protection. Do I have polyethylene casement on that pipe? Possibly not, if the pipe was installed in the 1800s. Do I have galvanic anodes? Did I install any corrosion control on this pipe down the line? Was a cathodic protection system installed after the fact or at some point during the life of that pipeline? Hydraulics, do I have any cement lining on the inside? Depending on the age, for sure. Was it lined in place using cement mortar lining or other types of linings throughout its design life? Also very important to understand, okay? And that will tell us a lot about hydraulic efficiency of that water main. And we could also have a pressure and flow rate monitoring system to understand that aspect better. We also need to look at soil resistivity, pH. So if we take a lot of soil samples in the vicinity of that water main, we could tell how corrosive is that soil to iron in general. Inspection, very important. Luckily, we're dealing with a metallic pipe. And metallic pipes, you could assess the condition of those mains. You could tell what's wrong with them. At least I could tell what's wrong with them. So leak detection, very important. Type of breaks, mechanical or corrosion related. Visual inspection could happen as well if you have access to that pipe. And measuring the corrosion is actually an indication of the remaining service life of that main. How do we assess the condition of water mains? There are so many, actually, ductile and cast iron pipe, even steel pipe, have almost every tool in the market would work on them. Why? Because they are made out of a metal. You could easily trace them, find them, and inspect them. You could do CCTV camera inspections, visual inspections, acoustic, electromagnetic, ultrasonic, and even metallographic analysis in the lab. CCTV cameras are evolving. They are getting better and better every day. So you could assess the condition of the main on the inside and look at cement mortar lining defects. If the pipe was lined in place, for example, look for any inconsistency, the validity of that main. So these are things that you could look at with a CCTV camera. Major defect. It won't tell you a lot about variations in wall thickness. There are better tools for that. Visual inspection, one of my favorites because I could see the pipe. However, one of the most expensive options because you have to cut the pipe, take it out of service, and inspect it, take it to the lab, clean it, sandblast it. So there's a lot of details that go with that type of analysis. It is recommended if you're taking that pipe out of service. However, if you're not, then there are better options. There are non-destructive and actually more economical. Soil corrosivity surveys, like I said, it gives you an evaluation of the area in terms of how corrosive is that soil to iron, and based on that, we could estimate what's going on with that water main, and we could actually not just estimate. This would indicate the possible status of that water main. This is one of the oldest installation. Actually, it is the first ever polyethylene cased water main in North America, installed in Lafourche Parish, Louisiana. Folks, this was installed in 1958. We dug up this trench 2 years ago after 60 years of service. And my colleague here is removing the wrap on that pipe after 60 years. You can see how the wrap, the polyethylene casement is installed perfectly on that pipe, snugly around the pipe. And while my colleague is removing this polyethylene encasement, you could see some rust on the pipe. This is a very corrosive environment. Swamps in the Lafourche Parish, 300 ohm centimeter soil, saturated soil with positive sulfides. So these are also called nasty environments. So perfect environment to test any corrosion control method on metallic pipes. So once we remove the wrap, like I said, you see surface oxidation. We expect that to happen, consumption of oxygen between the wrap and the pipe. However, we could clean that. So we use the wire brush and water and some water to clean it. I promise I did not Photoshop this photo. I was there, I took it. So the last step is actually tapping the pipe with a welder hammer to sound the pipe. And what we're trying to sound here is the ding and basically the sound of iron. So we didn't lose the iron. We were not left with graphite only. And that's actually the sound of iron after 60 years of service. So last step in every dig up, folks, when you do acid condition assessment is you access that pipe, you look at it, please put back the polyethylene encasement if the pipe is wrapped. So you could extend the longevity of that polyethylene encasement. Okay, because polyethylene encasement is a great tool, very effective, very economical. However, the installation is very critical as well. If you have inspectors in your cities, you want to make sure that they understand inspection, and I'm happy to help with any of that training as well. Understanding inspection and proper installation is a key for the success of polyethylene encasement. Ultrasonic testing, also commonly used for above ground applications or where you can access the pipe. It is a local inspection tool. They're getting better with trains and modular tools that you could pull inside the pipe, but they're not actually very practical in most cases. Metallographic analysis, we used to do those a lot before non-destructive testing became popular. In the past, I would say 30, 40 years. We take a piece of that pipe, sandblast it, take it to the lab, and our folks in the lab are always happy to see old pipe there because they could look at it and evaluate it. It is not as simply done these days due to cost of doing all of that. And we have non-destructive tools like acoustic testing and magnetic testing, ultramagnetic testing that could do the job for us. Acoustic is very good. It is evolving these days. Give us a good idea of variation and thickness of the wall of metallic pipes from ductile iron to cast to steel. Even it detects some air pockets in the system and any leaks. So they are very popular. They have some limitations, of course, in terms of accuracy. Electromagnetic testing, one of my favorite actually on a personal level. I like them because they are accurate. They give us a good indication on the status of that water main. They tend to be more on the expensive side of service. Why? Because you have to dig a hole and access those mains. If the pipe is a 6-inch or 8-inch, you probably could get away with access through water hydrant and collect those drains from another water hydrant. However, they tend to be more critical. So we're dealing with 12, 24-inch water mains. Then you have to provide an access point and a collection center for those electromagnetic trains. Very accurate, and they are excellent for telling you the condition of that main and the remaining thickness, so you could do reverse engineering and actually assess the longevity of that water main over the years. So why do we care about condition assessment and failure of iron pipes? For 2 reasons, actually 4 reasons. Operational, you don't want your team working on a Sunday night or on Christmas Eve fixing water mains. So that's why you do condition assessment and preventive maintenance. Economic, it costs a lot to call a contractor on Sunday afternoon than on a Monday morning. We all know that because I was a contractor at some point, and makes total sense. Socially, nobody wants the city and a contractor working on their street on a Friday afternoon or on a Christmas day. Environmentally, also, we want to make sure that the pipe we're cleaning and pushing through our system is getting to our customers and not lost in the ground. So water loss and water loss prevention is actually one of the biggest topics today from an environmental standpoint. So all of that leads to better condition assessment, evaluation of those mains, and a life extension tools that we could eliminate leaks, reduce their amount, and provide better quality water for our municipal clients. So when it comes to decision making after condition assessment and evaluation of the remaining thickness of the pipe, the status of that pipe, we could either make a decision with ductile and cast iron pipe. Especially I'm talking about cast, because here older mains are cast iron, newer mains are ductile iron. We'll either repair those pipes, rehab them, replace them, or if we're considering a new project where we're putting 24-inch ductile iron pipe, for example, transmission main, that's now we're talking about new installation. For repairs, you may have a local hotspot where corrosion is a local spot in this water main, and that's perfectly fine. You don't have to replace the water main. You go in, put a clamp on that main, and what I always suggest is putting an anode, attach that anode to that pipe, so you could extend the life of that pipe for another 25 to 30 years, just that stick of pipe. Keep in mind, every pipe is its own structure as far as corrosion is concerned, because ductile iron pipe joints are not bonded. So unless they are bonded by design, but by default, they are not bonded. So corrosion is unique for every structure. I mean by that, every stick of pipe. So also we could rehab. I did that for almost 3 years, did a lot of CIPP across Ontario and Quebec and New Brunswick. CIPP is a good tool, great option with metallic pipes, especially with ductile iron, cast iron, that were not lined back in the days. So if you have tuberculation issues with cast iron pipe, for example, you could easily flush them, clean them, and do spot repairs if you have issues with that, with tuberculation, or you could do mainline lining, and there are various options in the market today to do so. So you could extend the life of that main over the years for another 30, 40, or 50 years. If you decide to replace, there are obviously open cut options, the traditional expensive options, and there are less disruptive, less invasive options with trenchless technologies like pipe bursting and HDD. And I'm very knowledgeable about that, so if you have any questions, please let me know. For new installations, folks, and that's where what we're doing today with new water mains across North America as a ductile iron pipe industry. First, we analyze the size, the length, the thickness required for a new water main, and then we select the type of joints, the lining, gasket options. We analyze the soils, and we assess the risk of the corrosion-related failure down the line. So we use the design decision model that I will discuss in the next few slides. We do proper monitoring and inspection over the years to make sure that main is still in good condition. And I showed you an example of an inspection that we always do. Every 5 or 10 years, we go back, dig up a hole, and look at that pipe and say, it's in great condition. So inspection and monitoring is also important. The goal is to achieve 100 years of service. That's what we designed ductile iron pipe for today. We don't design for 40 and 50 years. We expect 100 years of service. So some of you may ask, well, ductile iron pipe is thinner than cast iron pipe. Does it fail sooner? And the answer is ductile iron pipe, true, it is thinner than cast iron, and the reason why it is thinner because the material is much stronger. So mechanics of material 101, stronger the material, thinner the wall of the pipe, plus the wall is flexible. So it is a flexible conduit that rerounds under pressure. So if you take that example, a pressure class 350 ductile iron pipe, we use that in distribution mains. So 350 psi plus 100 psi of surge allowance, that's 450 psi. We multiply that by 2 for a safety factor, that's 900 psi design pressure. For a 900 psi design pressure, all what you need is 0.14 of an inch. But every stick of pipe that we make, we add a service allowance of 0.08 inch. That's not structural, it's a service allowance. Now, we also add a casting tolerance because we're casting the pipes centrifugally. So to account for any deviation or changes in thicknesses during the casting process, we add a casting tolerance. Now my total is 0.28 inch, which is total. It's actually the double of the required structural thickness of the pipe. So if this has a safety factor of 2 and a surge allowance, how about 0.28? So yes, the material is thicker, but the material is much stronger and it has an extremely high inherent safety factor if we're talking engineering here. So the goal is not to rely on wall thickness to handle corrosion and buy time. We design for applied loads and we handle corrosion separately. That's the main key here. So internal protection, folks, like I said, every pipe is provided with cement mortar lining. Depending on the size of the lining, thickness may vary from all the way from 3 inch to 64 inch in ductile iron pipe size. There are other types of linings that we select in certain applications. If we're doing air pipelines, compressed air pipelines or hot air pipelines, we don't use any linings, for example. In sewer applications, force main applications, we may require protective 401 in some parts of that pipeline, and this is designed, that's actually a project-specific design that we could look at. There are other types of linings for other applications. So today, every application has its own lining, where back in the days, we didn't have a lining for those pipes. So things have evolved over the years. Make sure you select the proper lining for the proper application. So how about external corrosion? I told you polyethylene encasement is one great option. However, there are other types of corrosion control methods like zinc coating or cathodic protection. So how do we select the proper corrosion control on ductile iron pipe? So a few years ago, I would say in the past 2 decades, CorPro and DIPRA worked together, combined over 60 years of research and 60,000 data points, and we designed the design decision model. CorPro is a leader in corrosion control across North America. So we worked together on designing the likelihood and the consequence matrix. And what we're trying to achieve here is to select a proper corrosion control method for a certain project based on the likelihood of corrosion and the risk of a failure of that pipeline. So when you draw a line on the likelihood and a line on the consequence of corrosion, both lines will have to intersect at some point. If you end up in zone 1, 2, 3, 4, or 5, that would change your recommendation of that pipeline. So for zone 2, 3, 4, or 5, for example, they may have different recommendations. For zone 2, it would require for a V-bio enhanced polyethylene encasement. Zone 3, bonding joints and V-bio. Zone 4, that's when we talk about zinc coating and sacrificial anodes. And zone 5, that's the most advanced corrosion control, and that's cathodic protection. Okay, how do we assess the likelihood of corrosion? We take soil samples and we analyze the resistivity, the chloride, the pH, all of these elements of a soil, and then we account we account for the total points of that risk. The total points is 60. So if you were close to 60, that soil is very, very corrosive to iron. If we're closer to 10, for example, that soil is not corrosive. So if we take an example of 14, this is not a corrosive environment for iron pipe. We draw a line on the likelihood of corrosion, and then we assess the consequence of corrosion by studying the pipe size. Is it small, large diameter pipeline? Is it in downtown New York City or in a cornfield in Saskatchewan, for example? 2 different environments. Access to that pipe is different. Is it servicing a hospital, a firefighting station, or just one client on a farm? 2 different criticality of those mains. Depth of cover, is it accessible or not, and whether we have water supply or not. Once we assess all of these criticality aspects of that water main, we collect the total points. If we're close to 50, this main is very critical. If we're close to 10, that main is not critical, for example. So let's say we're 48. that's a critical water main. And we're still at 14. That means no non-corrosive environments. We end up in zone 2, and that means VBio enhanced polyethylene casement is enough to protect this water main for 100 years of service. However, if let's say we have a likelihood of corrosion of 32, which means in another case, those soils are corrosive. Now we end up in zone 4, and in this case, we may as well use zinc coating with VBio or sacrificial anodes on those pipes. Okay, so in other cases, let's say we have a high corrosive environments and a high critical water main. That's when we end up in a zone 5, and those are very rare, folks. They are like 5%, if not less, of the installations we put today, unless the city calls for a type 5 recommendation for every new water main. And that's very aggressive and very unnecessary, because it adds cost to a project that is not really needed, because you might be in non-corrosive environments and all what you need is a bag on the pipe. Okay. For new installations, you can install it using open cut installations or with trenchless options. I have a lot of experience with trenchless options, so if you have a question, I'm happy to help you. Obviously, the criticality of a trenchless application might be higher or lower than a standard open cut. If you're in a pipe casing and you have access to that pipe, that's non-corrosive environments. But if you're installing a pipe under a river and you can't see that pipe later on, that's a high critical environment, and we treat corrosion differently in terms of risk at that point. And it's not really dependent only on the type of soil we're dealing with. So trenchless might be a little bit different, and and those are very rare applications. We probably do 10-15% of our installations with trenchless, and the rest is mostly open cut. So installing polyethylene casement is very important as well. There are many ways. We don't have enough time today to go through how to install it properly, but just keep in mind, it is a very simple process. Basically, we put a bag on the pipe, we tape it every 2 feet, so the pipe is snugly installed around the pipe. We make up the joint, and then we overlap the polyethylene casement on the joint, and then we tape it again. So basically, we're creating a seal around the pipe. It's not watertight, like I said, but we're trying to create a homogeneous electrolyte around that pipe and a dielectric barrier between the soil and the pipe. Last few slides here that I have, AWA study that's very interesting, and if you don't have access to that, please let me know. Happy to share it. The AWA study, Buried No Longer, studied water main across the United States, and they actually estimated the service life of different pipe materials, actually all pipe materials used in water mains. And you could see for ductile iron pipe, you have 2 columns. You have a short service life and a long service life. And that was really dependent on whether the pipe was protected or not, and obviously the age on other factors. But what I'm trying to tell you here is, if the main is not protected and a water main with ductile iron is not protected, there's a good chance it will serve you for not 50 years. But that's not what our expectations are. We have high expectations from ductile iron, and we want to protect it so we could achieve a minimum 100 years of service. Okay. Another interesting chart that you see in the ISO standard for asset management guidelines of water system is this chart, where you see ductile iron pipe has a maximum and a minimum service life of various pipelines. But when it comes to ductile iron pipe, you see that if this pipe was not provided with any coating, that means cement lining on the inside, cathodic protection, or polyethylene casement on the outside, the pipe service life is around 60 to 80, actually from 40 to 80 years, on average 60 years. Okay, we don't want that. We want to be here with ductile iron pipe with polyethylene casement or zinc coating and cement mortar lining on the inside. So these pipelines will serve from 90 to 120 years, and that's what we want. Takeaways of this presentation: iron pipe has evolved over the years. It is, and corrosion control and protection has evolved over the years. Many cities across North America still rely on ductile iron pipe, although in your environment, if you're in Ontario, there's a good chance that you're relying on cheaper other type materials that are in the market. Asset management of ductile iron pipe relies on your ability to design, install, operate, and maintain your systems over the years, regardless of pipe material, to be honest. Active management of cast iron pipes, the stuff that we inherited from our grandparents, some were excellent, some didn't do very well. So we need to understand the data associated with those mains, accurately analyze them, and we actually need to collect reliable data, like I told you earlier. For new water mains, I strongly suggest you follow the design decision model. I'm happy to chat about it more with you. VBio enhanced polyethylene casement is a very effective corrosion control method. In some cases, we might need zinc coating, bonded joints, and other corrosion control method. And keep in mind, we design for 100 years of service. We want to achieve that service through proper corrosion control, installation, and asset management. Okay. With that, this ends my presentation today. I really hope you found it interesting. That's my contact information. Please feel free to connect with me, send me a note. If you're too shy to speak up and ask a question, I'm happy to hear from you. And any feedback, any comments are welcome. And now I open the floor for your questions. So thank you.
Thank you, Sam. Thank you for this informative presentation. You sure covered a lot of ground within 1 hour.
Yes.
We went over time a couple of minutes. I just want to remind everyone the presentation is recorded and will be posted on our website. I posted the link in the chat, and for those that asked questions, we won't be sending out continuous development hours or continuous professional development certificates. It's a lot of man hours involved in administering these. We don't do them for free webinars. We provide those for our courses, but I'm a PO member as well, so I know that the reporting is voluntary. So you can use our website to get all the information from on the presentations and webinars that you've attended, and report your professional developments.
I need to collect those too. I mean, so
you need to get on top of those.
I'll give myself a presentation.
And so for that, with that, we do have one question that came in, and from Joe Timmerman. Joe, if you're present right now, you can. I know he's put his hand up for to ask the question verbally. There you go.
Thank you. Can you guys hear me?
Yes.
Yeah, basically, I just want to know if DIPRA has recorded any life cycle activities like deterioration curves where you show the gains of the condition. Let's say, for example, you start your installation at year 1, you know that it's 100% in condition. If you were to do like some kind of coating, then at age 3 or age 5, you got probably like 5 points in condition, five points in gain condition. If you were to do like year 60, you would maybe polyethylene encasement. You do. Have you guys recorded anything like that?
Yes, we did. That's actually an excellent question, Joe, and let me rephrase it here for other folks on the call. Did we monitor corrosion rate on different corrosion control methods or pipe provided with corrosion control methods, and how do we understand the evolution of corrosion rate over the years from day we install it till end of life, basically, of that main? And the answer is yes. And what we did over 60 years, when we go in our test sites, we bury groups of pipes. So what we do is we bury 6 groups of ductile iron pipe. Each group has possibly 8 or 9 sticks of pipes. All of them are in the same electrolyte, so basically same soil, but some may have different corrosion control method. Once we bury all of them together, We come back after 3 years, actually, we dig up the first group. We evaluate the corrosion on that, on those pipes. Then we come back after 10 years, we evaluate the next group, then 15, then 20, then 30 years. And this is how we understood the evolution of corrosion rate and the effectiveness of polyethylene encasement on other and cathodic protection and zinc coating. Now, zinc coating, for example, has, and I'm going to give you an example. We compared zinc coating with bonded coatings. Those are polyurethane coatings, and polyethylene encasement and cathodic protection in the same environment. And we know the corrosion rate of each pipe with a separate corrosion control method on it. So yes, we have studied that in one of most aggressive environments like Everglades City in Florida, and we understand the evolution of corrosion rate. And like I said, corrosion will always occur. What you have to, because it is a natural reaction of every metal with its environment. If it was air or oxygen, water, or soil. However, the rate is very important. Is it 0.001 mils per year under polyethylene encasement, which lead you to a 200-year of service? And we do that by monitoring. We put probes under corrosion rate as well. Under the wrap as well. So we put corrosion probes between the wrap and the pipe, and we connected those to testing stations where we come back regularly and we measure the corrosion rate on that pipe. So there are advanced methods that we use in our test sites today where we evaluate corrosion, but I didn't have the chance to go through the details of, I didn't want to bore you guys with how corrosion works and how we monitor it over the years. But yes, we do monitor corrosion. We know that hopefully after many years, the corrosion rate should be steady. It peaks at the beginning. So year 1, year 2, we see a peak, and then it goes down and goes steady after a while as a corrosion rate.
Thank you, Sam.
Yeah, you're welcome.
So I wanted to ask you a question, Sam.
Yes, sir.
Very briefly, since we can cover it in a minute or less. What are the main reasons or that you think municipalities should consider investing in ductile iron versus other alternatives that are out there?
Yeah, that's a great question, and here we're getting into some politics, but there are many reasons why major cities across North America, I'm just giving you an example, Chicago, Boston, or New York City, or Vancouver, for example, rely on ductile iron pipe today, and they only install ductile iron pipe in the water system, where other utilities in Ontario especially, they allow every pipe material, so it's cost-based. Basically, the cheapest get the job. Generally, ductile iron pipe is not the cheapest material in the market because you're buying a Mercedes of pipe. If you want a Toyota, you get a Toyota. You're not going to get a Mercedes for the same price. What's really the difference is longevity. That's one, strength, and resilience. So when we talk about ductile versus other materials, first, hydraulic efficiency has the greatest inside diameter compared to other materials. So OD has to be the same for other materials. ID is different. So hydraulic efficiency tend to be different when you calculate pumping costs on a yearly basis. Second, we will look at longevity. We expect 100 years of service, not 50 or 40 like cheaper materials, for example. We also look for resilience. So if you look at every area across North America and Japan, for example, when they have earthquakes, they only use ductile iron pipe. And the reason why we use ductile iron pipe because of the joint deflection capability and pull-out capability, deflection. So and the resilience of the products, the resilience of that product in handling stresses and loads. Keep in mind that every pipe is as good as its bedding condition. And once you compromise that bedding condition, you're really reliant on that pipe material to do the job for you. So if bedding condition is compromised in an earthquake or any ground shifting or moving, even if you're doing tunneling in an area and you shift that ground you may cause a sinkhole in those areas. And that's when you have a lot of pipes fail, where ductile iron pipes' ability to handle pressure and the strength of that wall is astronomical. And that's why you go to Japan, they have 1,500 earthquakes every year, and that's what they use. Last reason is sustainability. Like I said, the longevity of that pipe. In some areas, you can't use other materials. So if you're dealing with contaminated soils, for example, you would have to use a metal pipe, and that's usually ductile iron pipe on the small diameter. If you're dealing with contaminated soils like landfills or soils contaminated with hydrocarbons, because other materials, for example, plastic, are permeable, and you'll get the hydrocarbons through the wall of the pipe, where ductile iron pipe is fully impermeable end to end. So there are many other reasons, but those are the core reasons. We could talk about tapping as well, safety with working that pipe, and actually the ease in installation as well. I know contractors like light pipes to carry around, but I don't think the excavator cares about the weight of the pipe. So we care more about the longevity and resilience and sustainability of those mains. And that's what major cities and engineers are doing these days.
Thank you, Sam. Thanks for detailing and answering my question. I'm sure the people that are listening to us live or through the recording will appreciate your input when they're making consideration between different alternatives in the future.
Absolutely.
With this, yeah.
Happy to answer any questions, folks. Feel free to reach out to me. That's my email. Happy to connect with you on LinkedIn, or so feel free to reach out, connect. Thank you, Amin, a lot for this, for inviting us to be with you today. Hopefully we get to see you guys all at the MEA conference next year. So keep up the good work. Amin, really appreciate what you're doing out there.
Thank you, Sam. And thanks for everyone for taking the time to join us. I'm seeing some familiar names in the attendance. Have a good rest of your day.
And talk to you soon. Thank you.